My project is on finding volume, or more specifically, finding the volume of integrals. Before we start finding the volume of something, shouldn't we first know what exactly it is we are finding? So the question we are asking is, what is an integral exactly? An integral is the calculation of the area between a given equation and the x-axis. There are two types of integrals. Finite integrals where you find the area with one point given and the other where the graph intersects it on the x-axis. The other type of integral is definite integral, where you find the space between two given specific points on the x-axis to solve for. In my project, we will be using definite integrals for the simplicity of it, with 2 points that are already given to us. And to solve for the area of the integral, you would use this equation. The next thing that you must know about integrals is that you can never find the exact area of one because it is an irregular shape. What you're actually doing is finding the area of an infinite amount of smaller rectangles all lined up underneath the equation and above the x-axis. We get the distance of the width of the equation using dx. But to find the volume, which is what we want to be able to solve for, by the end of this video, we will be rotating the whole equation around the x-axis. So as an end result, we would be getting this type of cone shape. So back to the rectangles formed by the integration method. If we were to rotate each one around the x-axis individually, we would end up getting something close to the shape of a cylinder, with the x-axis coming out of the center of it. So the next question we must ask is how to find the volume of a cylinder so that we would be able to then apply this method of finding volume to the integral. One thing that we all love is pie. I mean, who doesn't? It's a traditional dish that's been around for generations. Another pie that we should love is the mathematical pie. It's a never-ending, non-repeating number that shows up in nature naturally when something is rotated 360 degrees around an axis. So because we are rotating our equation 360 degrees around the x-axis, we will need to use pi in our formula to find the volume of an integral. Just like the cylinder with the center point representing the x-axis. So the last thing that we need to be able to find to solve for the volume of a cylinder is the height, because we know that the equation for solving for the volume of a cylinder is pi radius squared times the height. When we apply this formula to the equation that we want to find the volume for, we find the radius by the height of f of x, so when you plug the value of x into f of x, you get the height. Therefore, we leave f of x in our equation as the radius. And then the space between all of the other smaller rectangles is measured by d of x. So when you put the whole equation together, you place the pi outside of the integral symbol and be sure to square all of f of x, not just x. That is why we use this equation. So now that we understand the basics behind the math, let's try this on a real equation. For the equation, we will be using f of x equals the square root of x. It is a very simple equation and it gives us a nice line to follow along, with the fact that it will also make it very easy to simplify later on. The bounds that we will be using are 1 and 2 on the x-axis, and we are rotating the entire integral around the x-axis. Now we have to place all this knowledge into our volume of an integral formula. The lower bound goes on the bottom and the upper bound goes on the top. Once we have plugged everything into the equation, we can simplify it a bit by getting rid of the squared square root of x. So we are then left with just solving for x times dx between 1 and 2 multiplied by pi. Because we are solving for x times dx, we have to then find the antiderivative. The antiderivative adds 1 to the power of whatever the equation was set to, and then dividing it by the number of the power, which in our case is 2. Therefore, we have x squared divided by 2 as our antiderivative. So then we rewrite the bounds of our integral on the bracket. And don't forget about pi. You can choose to multiply the end product by pi if you would rather not use it in the antiderivative, but it's important not to forget about it. So then you solve it out by plugging the upper bound in first to the antiderivative and then having it be subtracted by, again, the antiderivative, but with the lower bound in place of x. You can think of it like subtracting the smaller number from the bigger number, because 2 is obviously bigger than 1. As a result of plugging 2 into the antiderivative, we get 4 pi over 2. And as a result of plugging 1 in, we get pi over 2. After we subtract them, we get the answer of 3 pi over 2 units cubed. Don't forget the units cubed part, it's very important. One last time as a review and for a reminder as for what we were solving for was the area between these bounds 1 and 2 for the equation f of x equals the square root of pi rotated around the x-axis, therefore its volume. And the end shape of the figure that we were solving for looks somewhat like this, with the slice at the 1 and 2 mark on the x-axis, and the volume of it was 3 pi over 2 units cubed.